This week we're going to talk about the Net Change Theorem. Now, the Net Change Theorem is an application of the second part of the fundamental theorem of calculus. And in words, the Net Change Theorem describes what happens when our function is a rate of change in the second part of the fundamental theorem of calculus. And it states when a quantity changes, the new value equals the old value plus the integral of the rate of change of whatever quantity we're talking about. And if our new value occurs at B and our old value occurs at A, as we've been doing in the second part of the fundamental theorem of calculus, this sentence translated into math is f of B equals f of A plus the integral of f prime of x dx, the integral from A to B. And of course, f prime is the rate of change of this quantity. This quantity is measured by f. So the new value equals the old value plus the integral of the rate of change. And of course, we can see this is kind of a restatement of the second part of the fundamental theorem of calculus if we just move that to the other side. But this is in the special case where f prime measures the rate of change of a quantity, and we're really looking at certain applications of this. And we'll look at 3 examples. First, a honeybee population starts with 100 bees. Okay? It increases at a rate of n prime of t bees per week. Okay? And the question is, what does 100 plus the integral from 0 to 15 of n prime of t dt represent? Well, we start with 100, and then this is considering the integral of the rate of change from time 0 to time 15. What is our time unit? Well, our time unit is weeks. When a quantity changes, the new value equals the old value, 100, plus the integral of the rate of change of that quantity. M prime gives us the rate of change. It's positive because that increases. So what does this represent? The bee population, the new value, after 15 weeks. So I'll just write that here. Bee population after 15 weeks. Now, that type of example is just really a retranslation of the statement. An example you're more likely to see is one involving velocity. That's been the rate of change we've considered most throughout the semester, so it's the one you're most likely to see on a final exam. So let's look at this example. A car moves north at 40 miles per hour between 2 and 4 p.m. The car moves south. That looks like ear. That's car. The car moves south at 30 miles per hour between 4 and 5 p.m. Okay? Find the net displacement and the total distance traveled. So we need 2 different things here. We need the net displacement and we need the total distance traveled. Traveled, of course, with 1 L in American English, between 2 and 5 p.m. Well, we have 2 things to find. We can actually find these in this example without using any calculus. Like if we just look at what's happening here. Car moves north 40 miles per hour for 2 hours. So it goes 80 miles north. Then it goes south 30 miles per hour for 1 hour. So it goes 80 miles north and then 30 miles south. Find the net displacement. If you go 80 up, 30 down, you're 50 miles up. So 50 miles north. Find the total distance traveled. Well, between 2 and 4 it goes 80 miles. Between 4 and 5 it goes 30 miles. So that's 110 miles. But we would like to do this with calculus. And in the example after this, it would be quite difficult to do without calculus. So how can we do this using calculus? Well, for net displacement, we can use the Net Change Theorem. So let's say net displacement. I'll abbreviate displacement DISP. Well, the Net Change Theorem, we can assume at 2 o'clock that this car is at position 0. So we can assume that this first value is 0. So the new position, the net displacement after 3 hours, would be given by the integral from 2 to 5 of our velocity. Remember, velocity is a rate of change. And we're given a velocity function. But how can we do this integral? Moves north at 40, moves south at 30. That's two different velocities. Well, what we can do is split this integral. We're looking between times 2 and 5. We can split this integral. You could also define 2 o'clock to be 0. I'm going to keep the 2 and 5. Just because, well, I knew we were going to have to split it eventually, so I didn't want to have to think of 0, 2, and 3. But the velocity, notice, is a function which changes at time 4. So we can split this integral from 2 to 5. This is how you would do a piecewise integral for a piecewise function. We can split this into the integral of the velocity from 2 to 4 with respect to time, plus the integral from 4 to 5 of the velocity with respect to time. Now, what are these velocities? Remember, velocity tells you what? It's the change in position divided by a change in time. Well, in order to describe that, we would need to define a positive direction. So here, I'm just going to define north to be our positive direction, and then, of course, south would be the negative direction. Notice, if we went north and then west, it would be a little different, because it wouldn't be a positive and a negative direction. But here we have north and south. So we'll define north as our positive direction and south as our negative direction. Well, the velocity going north from 2 to 4 is 40. So this equals, I guess I'll write it over here, equals the integral from 2 to 4. Now I'll write it over here because I'm not positive I'll have enough room. So this equals integral from 2 to 4 of 40 with respect to time, plus the integral from 4 to 5, the velocity from times 4 to 5, south at 30 miles per hour. Well, that's our negative direction, so we would need negative 30 with respect to time. And now we just need to evaluate this interval. Well, first thing would be what? 40 t from 2 to 4. The next thing would be negative 30 t from 4 to 5. 40t from 2 to 4 is 80. 40 times 4 minus 2, 40 times 2 is 80. Minus 30 times 1 gives you negative 30. 80 minus 30 is 50. So overall, the net displacement is 50 miles in the positive direction, so 50 miles north. If you define south to be your positive direction and north to be your negative direction, you would get negative 50. And of course, that would also be the same answer, because with north as the negative direction, if you go negative 50, if you have negative 50 as your net displacement, well, then you're 50 miles in the negative direction, which would be north. But here, define north to be positive, define south to be negative. Net displacement is 50 miles in the positive direction, so 50 miles north. Now, what about the total distance traveled? How can we do that? Well, let's look at a graph. Right here we have a graph of the velocity on the y-axis, time on the x-axis. Between 2 and 4, the velocity is 40. Between 4 and 5, the velocity is negative 30. And what did we find, or what does this integral find? Well, remember, the integral gives us areas. And notice this net displacement is given by that area, which is 80, minus this, excuse me, minus this area, which is 30. And that's why the integral of our velocity function gives us the net displacement because the integral treats areas below the x-axis as negatives. But if we want to find the total distance traveled, well, how would we do that? We wouldn't treat this area down here as a negative. We would want to treat the area down there as a positive. Excuse me. It's always good to have lots of water. For those times when, for some reason, your voice stops working. Where was I? To find the total distance traveled, we would want to treat this as a positive, because you're still traveling between 4 and 5. Well, how can we do that? There are a couple ways you could do it. I think the easiest way would be to still take an integral, but we would want the integral to treat this as positive. Well, how would we do that? We would want that area in our integral calculation to be above the x-axis, so the integral treats it as a positive. Well, how do we take something below the x-axis and move it above the x-axis? Well, you take the negative of it. In this function, that would correspond to turning that 30 into a positive. But in general, what we're doing here, when we want to take things below the x-axis and move them up, is we are taking an absolute value. So to do the total distance traveled, 1L, we would take the integral of the absolute value of the velocity function from 2 to 5. And again, this velocity function, even if we move that above, is defined piecewise. So it would turn into the integral of, let's say, 2 to 4. Let's split it before taking the absolute values. Plus integral 4 to 5 of absolute value of v of t dt. The absolute value of v on 2 to 4 is 40. The absolute value of v of t on 4 to 5 is the absolute value of negative 30, which is negative 30, which is also positive 30. And we would have this computation just like that. It would then become 80 plus 30. Well, not just like that. It would become 40t and 30t, but they would be added. 80 plus 30 is 110 miles. And in this case, we don't have a direction. We're just looking at the total distance traveled. In the net displacement, there was a total distance, or there was a direction to think about. In this one, there isn't. Let's look at one more example with a more complicated velocity function. Here, given velocity v of t is 3t minus 5 feet per second, find the net displacement and total distance traveled from time 0 to time 3. Well, let's do net displacement first, because net displacement, all we have to do is take the integral. Total distance traveled, we're going to have to take the integral of the absolute value, which is much more complicated, as we'll see in this example. So let's do net displacement up here. Net displacement. Well, it's the integral time 0 to time 3. Again, we'll define it to be at position 0 times 0. Net displacement integral 0 to 3 of our velocity function, 3t minus 5 with respect to time. When writing an integral, I always like to write this in parentheses times dt, because technically it is being multiplied by that. In a sense, it's being multiplied by that, I should say. So let's do this integral. 3t would be what? 3 halves t squared. Negative 5 integral is negative 5t. The derivative of this is 3t minus 5, so that checks. From 0 to 3. At 0, we get 0 minus 0, so all you really have to do is evaluate at 3. So we get 3 halves of 9. 3 halves of 9 is what? 27 halves. Minus 15. Uh, 15, of course, is 30 halves. So 27 halves minus 30 halves is negative 3 halves. And our units are feet here. So from time 0 to time 3, whatever this function is measuring the velocity of moves 3/2 in the negative direction. 3/2 of a foot in the negative direction. Now how about the total distance traveled? Well, we know to do total distance traveled, we would need the integral of the absolute value of our velocity function, again on 0 to 3. But how do we do that? Well, in the previous example, it was clear where the velocity was positive and where it was negative. In this one, it's not immediately clear where the velocity is positive and where it's negative. So let's look at the velocity function. You don't actually have to draw this to figure it out, but it is useful to figure it out. Let's remember, we're concerned with what happens between time 0 and time 3. So this is our velocity, and this is our time. This is not a position on the y-axis, velocity on the y-axis. We're looking at the velocity function because that's what we're integrating. This is a line with y-intercept down here at -5, slope 3. So here's our velocity function. So v of t is 3t -5. And when we integrate the absolute value, what we're really doing is splitting it where it's positive and where it's negative. We're splitting it at the point where it changes from positive to negative. And then what we do to take the absolute value is, as before, we took negative of -30. Here we're going to take negative of 3x, or of 3t minus 5 on the piece where it's negative. So what we need to do is find this point. How do we find that point? Well, that's the point where it intersects the x-axis. What happens when it intersects the x-axis? It goes over something and up 0. So it goes over a t value and it goes up 0. So the y value, the velocity value, is 0 here. So all we have to do is set 3t minus 5 equal to 0. Add 5, divide by 3, and you get t is 5/3. So that tells us part of what we want to know. That tells us that this integral splits at 5/3. Haven't taken an absolute value yet, so we leave the absolute value on until we take it. But we do know it splits at 5/3, because that's where it goes through the x-axis. Well, the next thing we need to do is take the absolute value of our velocity function. Well, this graph makes it clear where it's negative and where it's positive. So that would tell us on 0 to 5/3, on 0 to 5/3 it's negative, so our velocity function 3t minus 5, we want the absolute value of a negative. Change all the signs around, and you get 5 minus 3t. Take a negative of that. You could write it negative 3t plus 5 if you want. After 5/3, the velocity is positive, so the absolute value is itself. What's the velocity? 3t. That 3 has too many humps. 3t minus 5. Well, and now we just have to compute this integral. Let's do that. Let's just finish this off, and then I'll explain what I was about to explain. Well, here, the integral, we get 5t minus 3/2 t squared from 0 to 5/3. These computations can get pretty annoying. They can get pretty annoying. Plus 3/2 t squared minus 5t evaluated from 5/3 to 3. There are some minor shortcuts you could do in this computation. I'm not going to do them. You could make observations about the absolute value. I'm not going to do it. I'll just do it directly. At 0, this is 0, so we don't have to consider that. Well, we do have to consider that. We subtract 0. So I'm not going to consider it. At 5/3, you get 25/3 minus 5/3 squared is 25/9 times 3/2 gives you what? The 9 and the 3 make a 3 and a 1. So you get 25/6. Plus what happens over here. So plus, evaluate at 3, you get 27/2. When doing this, you should get some of the same numbers over here. Well, you should get both of the same numbers over here. Minus, evaluate at 3, so minus 15. But then we subtract what happens when we evaluate at 5/3. 3/2 times 5/3 squared, we did over here, was 25/6. In this case, we have a negative of a positive 25/6 minus 5 times 5/3, so minus 25/3. Now, I would strongly recommend against jumping straight to a common denominator here, because there are some observations we can make. Now, you can add in whatever order you want. You don't have to go this, then this, then this, then this, then that, then that. You can observe, hey, look at this. We have a 25/3 and another 25/3. 25/3 plus 25/3 is 50/3. Okay, so that took care of that number and that number. What else do we have? We have a negative 25/6 and another negative 25/6. Negative 25/6, if you have negative 25 of something and another negative 25 of that same thing, you have negative 50 of them. So you get negative 50/6. Those have 2's in common. So that's negative 25/3. So that took care of that number and that number. 27/2 minus 15, I'll combine them here. That's a 3/2 again, negative 3/2 again. Well, how do we add these? Well, again, I would not jump to common denominators. I actually never jump to common denominators with numbers because, as we'll see in a moment, there's an easier way of doing it. 25/3, or 50/3 minus 25/3. If you have 50, you remove 25, you're left with 25 of them. Minus 3/2, and this equals 41/6. How did I get 41/6? Well, cross multiplication. 50 minus 9 over 6, so 41/6. And this is feet. So you can see the absolute value computation is much more annoying. One last observation I'd like you to make about this one. Suppose you didn't have a graph of the velocity function. How would you know how to split this integral? Well, you'd still start off by figuring out where the velocity is 0. So set velocity equals 0, you get 0 equals 3t minus 5, t equals 5/3. And you'd still split it like this. But then how would you do the absolute value? Well, you'd need to figure out what does this 5/3 tell us? This velocity doesn't have to be a line. But all this 5/3 tells us this is a continuous function. This 5/3 tells us that this function goes through the x-axis at 5/3. It also tells us it doesn't go through the x-axis anywhere else, so it's not going to do something like this. All we know from this is that the velocity goes through the x-axis at 5/3. Well, to do the absolute value, all we then need to find is if it's like that, or if it's like that. And to do that, all you need to do is check a couple points. So check velocity at, say, 1. You could use 0. I would steer clear from using the endpoints. But to figure out which piece is positive or negative, check what happens at 1. And over here, we don't want to check 3 because that's an endpoint. Well, we really could because of this, but I would avoid that. And then check velocity at 2. Velocity at 1 is negative 2. velocity at 1 is negative. So that tells you that the velocity function is negative on 0 to 5/3. Velocity at 2 is positive 1, so that tells you velocity is positive. And that tells you that the absolute value of velocity is itself. And the absolute value of velocity on this piece, I think I forgot to say on 5/3 to 3. That tells you the absolute value of velocity on 5/3 to 3 is just the velocity, because the absolute value of a positive remains the same. But over here, where it's negative on 0 to 5/3, the absolute value of velocity would be the negative of the velocity function, negative 3t plus